we can get started. Good morning or good afternoon, everyone that managed to join. I'm very happy that many of you could join us today on the occasion of the World Quantum Day. My name is Chiara Decaroli. I'm a PhD student in quantum computing at ETH Zurich. And today I'm joined by our two guests, Professor Yiwen and Professor Renato Renner. Yiwen, she's leading the hybrid quantum systems group at ETH, and she's researching different quantum objects and how to connect them and make them interact together. While Renato leads the quantum information theory group at ETH, and his research really spans many aspects of quantum information, from quantum computing all the way to foundations of quantum mechanics. The event today will have two different parts. In the first part, I will be interviewing Yiwen and Renato. We will have discussions about their personal journey through quantum physics, but also their research. And in the second half, we will welcome all questions from the audience. So feel free to interact at all times. Lydia Del Rio, who's a senior researcher in Renato's group, will be moderating the chat both here on Zoom and on YouTube. So feel free to send us the questions, also any clarifications that you may have during the talk. She will get on it. Great. So with that, I think we can get started. And I want to start us off with a bit of a silly question. And so I want to ask Yiwen about a hypothetical scenario. Let's imagine that you are at a dinner party and you've just met someone completely new, and you've introduced yourself and you've told them, I'm a professor in quantum physics. What is their reaction? Are they in awe or are they terrified?
Yeah, so this has definitely happened to me. On airplanes and things like that. I mean, usually I think people think it's pretty cool. And I think nowadays a lot of people have heard about, quantum physics and quantum technologies. And so, yeah, I mean, people usually are very excited and they ask me to tell them more, so which is great.
That's great to hear. And what about you, Renato? Are you familiar with this experience as well?
Yes, very much, yes. It's always an emotional answer, I should say. Some people are terrified and others are amazed, but there's almost no one who is neutral. I mean, the usual reaction is, wow, that's cool, but I don't understand anything.
Yeah, so let's hope that with this event, we try to address the people that don't understand or that are afraid of the quantum. So yeah, great, thank you. And today we have a very diverse audience that is joining us. And I believe that many of them would be interested in hearing about your personal path and your journey in quantum physics. And so I want to get us started with the very beginnings. And so maybe, Yiwen, could you tell us when was the first time that you got interested in physics and what got you passionate about quantum physics?
Yeah, well, I think the question of when I or anyone gets interested in physics, it's a little bit hard to define, right? I mean, if you ever asked yourself why the sky is blue or why a train sounds different as it approaches you, it's, that you're interested in physics, right? And so, and I think a lot of, at a very young age, a lot of people are interested in physics and maybe don't realize that's what it is. But so, I can't say a definitive time when that happened. I think when did I become interested in becoming a physicist? Maybe that, I think happened maybe in high school. I had a really amazing physics teachers when I took my first classes in physics, and they were just, they made it seem like such an exciting and engaging topic. And also, maybe this is unusual for high school, but all the students, they loved this physics class because the teacher was amazing, and he got them really excited about it. And so, it was like cool to be a physicist. And so, from there on, I was something that I was, I sort of thought, this is something that I would like to do. And then in terms of quantum physics in particular, that was sort of toward the end of my bachelor's years. I tried out a bunch of different fields in physics. And I think quantum physics was sort of the thing that really attracted me, because it was really, partly just the day-to-day work that you do. I like that the experiments involved you building things that all, fit in a room or on a table, and you know what all the parts do, and you could change something and it will go and control some aspect of an atom or something that you can't see or touch. And I just thought that was really neat. So I think, toward the end of my college years is when I really got interested in quantum science.
That's awesome to hear. And we'll also get into the details of what a quantum scientist does later.
Yeah.
And so I want to ask the same question to you, Renato, and maybe can you share with us your earliest scientific thought, whatever that means?
Yeah, maybe it was a bit similar to what Yiwen said. I somehow had thoughts and didn't realize it's physics. I mean, my parents were not in academia, and I didn't even know as a child that physics exists somehow as a discipline. But I really got interested at some point into these perpetual motion machines. I always thought there must be a way to kind of generate motion or energy without investing in something. And then, of course, I somehow then realized as I grew older that this doesn't exist, and some people are claiming it doesn't exist. But then somehow I was always puzzled by this fact that I kind of knew as I grew a bit older that there are these little atoms that move around. And I always thought, but that one should be able to exploit. One could just have a little wheel with a ratchet on it, and every time an atom pushes on it, it will turn in one direction, and so you could actually create energy. And of course, that's an old idea. It has to do today, I would say this is really Maxwell's demon paradox that I was thinking about in retrospect. And actually this thought really, or this explanation, why does this not work? I was kind of always convinced it should work, persisted during my physics studies. So I never learned during my studies why this cannot really exist. What really speaks, I even tried with Lego to kind of have a big model of that, like a big wheel, and the atoms would be little billiard balls, and I could kind of prove for myself that it worked if everything was larger and not atoms. And I think only later then, I mean, I think this really moved to what I got interested as a researcher in the connection between thermodynamics and information theory. And that finally, this was for me a big moment when I finally understood why it cannot work. And it was even more exciting because it was an understanding that came from a completely different angle from information theory. So yeah, this was really like a long path. This question occupied me almost since my whole life.
That's really awesome to hear, and all the history behind. Yeah, that's great. And so we heard from both of you the very beginnings and your passion when you were kids. But then what happened after? So what happened after you, for example, Yiwen, when you got into physics in your bachelor's? And then what was your path after that? So how did you go from being an interested bachelor student all the way to becoming a professor in quantum science?
Yeah, well, so I mean, as I said, I sort of realized at the end of my bachelor's, I was interested in quantum science, that I wanted to do research in it. I wanted to be able to explore, my own ideas and build my own experiments. And so, I guess there is a pretty well-defined path to doing that and becoming a researcher, becoming a professor. But, I have to say that there were a lot of things that were unexpected along the way. I think, at the end of your bachelor's, you don't really know what it means, right, to be a researcher. Like there are so many aspects of it that you don't see when you're, learning about physics in the classroom. And so, even though I think I had a pretty clear goal in mind, there were surprises along the way. And there were definitely times when I wondered if this was the right path for me. It was not just a straight line. I just went for it, right? Like there were times when I definitely thought about these things as I learned more and more about, all the different things that are involved in doing science, right? And it's so different from doing physics problems on a homework, right? And so I think that's something along the way I really had to keep an open mind and adapt in order to get where I am now.
Great. And And for you, Renato, was it also something like this? Not really a straight line, many different curves. And was there anything that you would have done differently?
When I today talk to young students, they often tell me they couldn't decide between physics, mathematics, and computer science. And it was really the same for me. As a high school student, I could actually do everything. But then I had a math teacher who told me somehow I shouldn't do computer science because this is just about what people invented. And physics is really about how nature is. I mean, incidentally, later during my studies and actually after them, I met Ernst Specker, a mathematician, who told me physics is not interesting almost for the same reason, because this is just how nature actually is. But mathematics is much more interesting because it's how nature could be. So I didn't mind all these statements. I was always interested in all the three disciplines. And I think I was lucky that I could really do all of these. After my studies as a physicist, I did a PhD in computer science, so I could catch up on these things. And I was really always fascinated by the concepts that enter there. And now I'm back in physics since a long time, and I'm very happy to be back in physics, probably for the reason that my math teacher told me. This is really about nature, and I think that's what interests me most deeply. But I had really a winded path. So if you ask me what I would have done differently, I think my conclusion would be I would have ended up probably in a very similar position, even if I had done things differently. Because many things, like in Yiwen's case, were coincidences. I had this teacher who told me that and so on. But I think I had this deep interest in physics always and in the connection to computer science. And I hope that whatever path I would have taken, I would do research in this area still.
Very, very interesting. Thank you. Great. So maybe now that we've clarified a bit your motivations and your passion, maybe we can dive a little deeper into the quantum physics. And I want to propose a little exercise. So maybe Yiwen, maybe you can get started. Could you try to explain what is quantum science in a few sentences to a high school student?
Sure, I could try and think back to when I was in high school. Well, I guess at that point you've learned a little bit, right, through your science classes, maybe even taken a physics class, but it doesn't really matter whether it's physics, chemistry, biology. You've learned about sort of the laws of nature and how they govern the world around us. And maybe you start with the things that you can see and touch and you experience in your daily lives, and you've maybe done some projects or experiments in your classes, right? You've built something and made something or measure something using the knowledge that you now have about how the natural world works. And quantum science is in some sense just an extension of that. But now you have new things that you can play with, things like atoms or electrons or light, or usually very small things, but not always. And these things behave according to different rules, right? These are the rules of quantum mechanics, and they're different from the rules that govern the things that we see in our daily lives. And why wouldn't they, right? If you really think about it, why would an electron not behave the same way? Why would an electron behave the same way as a bowling ball or something, right? So and so you have to work a little harder to understand this new world. But once you do, now you have all these new toys, right, to play with, and you can do the same thing. You can study them, understand them, and even build useful things out of them. And because you have access to all these new objects and new rules of quantum mechanics, that's what makes it so interesting and fun, right? You can really do new things that you can't do in what we call the classical world, which is the world that we experience and live in. So yeah, that's, I guess, how I would describe it.
Yeah, it's awesome. I like both the playful aspect and the novel aspect of quantum. Great. And so now I bounce the same exercise back to Renato. And could you do the same, but this time explaining to someone like your parents?
Yeah, I would have preferred the other question, because I have actually a 15-year-old son who always sees me drawing these very nice formulas, and he gets very excited and asks me, what is that? But maybe actually you told me that you will ask that, and I tried to turn the question around, and I asked him what he got from all my explanations, how he would explain it. not now to me maybe, but to his grandparents, which would be my parents. And I think he said that if you zoom in, then you find that things are not continuous, but they're always little packets of stuff. So there's just fixed units. That's what he got from it. But these things behave very differently from what we would expect. And I think this is really like the explanation that I wanted maybe also to convey to him. So I'm happy it bounced back. But I think the amazing thing is, like Yiwen said, we have, like, physics is not that boring that if you zoom in, things always look the same. We get into a completely different world, so to speak, with different rules. And the amazing thing is we can understand these rules, maybe not why they are there, but what they do, and we can do calculations and all that. And of course, now to really understand them, I always tell him, you still have to study physics. Maybe that's not what I would tell my parents, but to him, certainly.
Great. So hopefully our audience now has a bit of understanding, if they don't have a background in science, of what we mean with quantum science. And so maybe we can then move to something more concrete. So maybe, Yiwen, can you tell us how a day in your life as a quantum scientist look like?
Yeah, well, as an experimental physicist, I would say that one of the nice things about that is that there's no sort of typical day, right? You know, on Monday I could be an electrician, not a very good one, but you know, and then on Tuesday I'm a computer programmer. On Wednesday I'm a plumber. And then on Thursday, I sit and write a bunch of equations and stare out the window and think about things, you know. And then on Friday, maybe, I don't know, I write grants or papers or things like that. So there's a lot of variety in being an experimental physicist. I like that. You learn a lot of different things, a lot of skills also, actually, that are useful in everyday life, actually. So yeah, I mean, a typical day is can vary quite a lot, actually, and that's what makes it really fun.
Yeah, I can totally sympathize with that.
Mm-hmm.
That's also how my days look like. And Renato, what are the 3 things that you enjoy the most about your job? It's a little different because you're a theoretical physicist, so.
Yeah, I think maybe the really nicest thing is that I can almost the whole day be together with people who are much more intelligent than I am and talk to them and think about science. And maybe, I mean, I told you before that as a teenager, I was thinking about these questions, how to build a perpetual motion machine. So this job really allows you to just continue thinking in this direction. So the things I would anyway wanted to have thought through, I can now do as a job in some way. But if you ask me 3 things, and I mean, usually when we hire people, we tell them, look, when you do research here, then there are at least 2 very important aspects, research and teaching. And I think these are really, apart from having the intelligent people around, the 2 main things, that we can really go into a territory. As a theoretician, we can also do that. I mean, just do it in our thoughts where no one has been. And I think this is really amazing in some way, to think thoughts that no one has thought before. And the other thing is the teaching. And I think to convey these things, to convey the amazing, let's say, facts about how physics is really a pleasure, in particular if you have bright students, and we definitely have that. So I think, yes, in that sense, really an amazing job. So I cannot complain at all.
That's extremely inspiring to hear. Very nice. And so we talked about the nice things, the things that we like, and what are on the other side some challenges that we face. For example, Yiwen, what are the challenging aspects of your job?
Yeah. So I guess also, as Renato said, you know, as a physicist, you work a lot with other people, right? I mean, it's really not a thing where maybe this is a stereotypical view of what a physicist does. So they you know, sit around and just think about things, right? But no, it's actually, you talk to people, you work with them, and that's just a huge part of the job. And this is something that I am learning to do now as a professor who, you know, I haven't been one for very long. And that's something, and you know, I'm starting to, you know, have my own students and learning how to work with them. that's, that's a new challenge that I am facing now at this part of my career is understanding how to motivate them, how to explain things to them, how to get them to work with each other. And so, that's maybe not a very physics thing in and of itself, but it's such an important part of doing research. And everyone thinks about physics differently, everyone works differently, everyone comes to it with different motivations and expectations. And so that's something that I'm really starting to realize and understand, how to basically manage a research group. And I think that's really important aspect of research that maybe a lot of people don't realize.
Yeah, definitely. And what about Renato? How did this COVID pandemic affected your research in the last year?
Yeah, that's a good question. So I think at the beginning, it was almost a bit of relief because many duties just went away. I had so many travels planned and stuff that would actually have been quite stressful. And suddenly I had a lot of time to think. But I think now, after a year, I really realize how much we need the personal presence, the personal interaction. And I don't mean the Zoom interaction, but the real personal interaction to actually have creative ideas, to just be there in a room and sometimes not say anything. I think the strange thing with Zoom is that you cannot be there and not talk. And if we are in front of a blackboard, we sometimes just stare at the formulas and don't talk. And this creative, let's say, being together, this is very difficult to emulate without being actually together. So I think now after a year, I have learned how much value is in that personal interaction. And I hope we can soon return to a mode where we can profit again from this possibility to actually discuss in a group and see how the others are thinking.
Yeah, definitely. As you mentioned, for you, being able to interact with many people is so central that I can definitely see how difficult it must be when we are only able to see each other on Zoom. And yeah,
I mean, I always knew it's central, but I think this year has taught me that it's just even much more important than I ever believed.
Yeah, that's interesting, and yeah, it's also great to have this realization thanks to the situation, of course. So then I want to move on to more your research topics, and so now I would like to really understand the gritty-nitty and the details of what you guys do in your everyday job. And so maybe Yiwen, you can tell us a bit more about your experimental focus.
Sure. Yeah. So I guess as Chiara mentioned earlier, what our group does is that we take many different types of quantum objects. So if you think about things that live in this quantum world, there are many different things. There are atoms, there's light, or what we call photons, which are particles of light, and electrons. And we sort of try to combine them together. And so in particular, we work with circuits, electrical circuits that behave quantum mechanically. We work with light, and we actually also work with mechanical objects, like things that move. And it turns out those can also act quantum mechanically, even though this is one example of a thing that's maybe not necessarily so microscopic, but it's really cool that they can also have they live in this quantum world as well. And as you can imagine, right, even if you don't know exactly how an atom works or a electron works or how light works, you can imagine they're very different objects, right? They have very different properties, and they each kind of do their own thing and have their own unique properties, right? That we want to maybe use or study. And so what we do is we try to combine them. We try to get them to talk to each other, which they don't always want to do. And so it requires a bit of work. But then from that, you can build really interesting things, right? I mean, if you think about some of the technologies that you use in your daily life, right? There's if you think about a computer or the internet, right? You have circuits that do computing, but then you transmit information over optical fibers, and there's links between these different objects. And in the quantum world, it in some sense could work the same way, right? So you want to have these very different objects talking to each other. So that's sort of the basic idea of what we do.
Awesome. And what about you, Renato?
Okay, I mean, we are really working on many different things, from applied topics like cryptography to foundations. And maybe to start, or maybe I just make 2 short points, one about cryptography. So in cryptography, what you have to do, or in quantum cryptography, you want to somehow prove that something is true. For example, that a message cannot be read under any possible circumstances of what, for example, an adversary who wants to listen to that message could do. So what you have to do is you have to first of all think of what are all physical possibilities of what an adversary could do. So it's a kind of modeling. You have to understand what does physics allow us to do in principle. And then you have to come up with a proof and show that despite all these possibilities, this message is still secure. So in order to do that, we need techniques, of course, from different fields, from computer science as well, in addition to physics. But then, and this is sounds like a bit disconnected, we're also doing foundations, but there's a very close link actually between these technological applications and foundations. Maybe I'll not go into that link, but talking about foundations, I think quantum mechanics has been a little bit a victim of its own success, in the sense that we could do so many exciting things. We could develop like almost everything that we have today in technology, like superconductors, I mean, even semiconductors that we are using for conventional computers. This is all based on our understanding of quantum mechanics. And somehow it got forgotten that in the very early days, people were very puzzled by the question that if they extrapolate the laws of quantum mechanics to larger systems, then some very strange things come out. I mean, one example is this famous Schrödinger cat, which is in a superposition between dead and alive. And this is just a consequence of taking the rules seriously and apply them to a large object. Now, the question of whether this actually is relevant or not is still, or even more relevant now, because 100 years later, we know quantum mechanics is an extremely accurate theory. So there's no reason to believe it's wrong. But if we really still consequently apply it to large objects, something comes out that is really against our intuition and daily life experience. And a lot of my foundations research is about understanding this, to try to come up with thought experiment, for example, to show that if we really do that, if we extrapolate quantum mechanics to large systems, we really run into contradictions, which would be a hint that there is some new physics as we go to larger scales that is not yet covered by quantum theory. So this is, we are essentially exploring this large size limit of quantum mechanics, but not with experiments, but with thought experiments, so to speak.
Yeah, thanks. So both of you actually used many different words in your explanations, and I'd like you to pick your favorite technical word from your field and maybe try to explain it to all of us.
Do you want to go first, Renato, this time?
Yeah, whoever wants to go.
Okay, my favorite term as a quantum information theorist is entropy. So what is entropy? Actually, there's this anecdote that entropy is a term that is used in information theory, and Claude Shannon, who introduced it because someone else told him that no one knows what it is, but it sounds good, more or less like that. I don't exactly remember the wording. And so what entropy, I think the amazing thing about this term is that it was introduced into completely different disciplines. Once in physics, and in physics it was coming in from thermodynamics, when people studied steam engines in the very past and they asked themselves what is actually possible, what's their efficiency, and it was defined in terms of notions like heat and temperature. So it was really something that is very tangible in that sense. And in information theory, it was introduced in a very different way. It was about the compression of data. How much can you compress data? So you would think this has nothing to do with each other. Why should a steam engine and the efficiency of that and heat and temperature have anything to do with compression? And so entropy has really these two meanings. So in information theory, the entropy, for example, of a movie tells me what's the minimal size to which I could compress the movie if I had an optimal compression scheme. And I think only relatively recently, in the last, let's say 20, 30 years, people started to understand why this is actually really the same. So formally, it always looked the same. When you put the two things into a formal expression, they look strikingly similar, but people didn't understand why. And now we understand that. And I think that's really why it's my favorite. It's a term that came from two sides, but their connection between the two gave us an enormous understanding, which actually is also an understanding connected to what I said before about the perpetual motion machines that I was trying to find.
You definitely have a very strong fil rouge.
Right, yes.
And Yiwen, do you have your favorite?
So actually, one of my favorite words, which is a made-up word, is not really even a real word at this point, and it's related to one of the things that Renato mentioned earlier. This word is macroscopicity, which I don't know if it's actually in any dictionaries, and it's this vague concept. I think still kind of vague and not so well defined. Although I guess Renato is working on making it maybe a bit more well defined. Is this idea of the quantum world extending into the macroscopic world and what happens then. And there are many ideas about what could happen, and it's confusing, as Renato said. And we are, it's very related to what we work on. As I mentioned before, we actually work with not so microscopic quantum objects, and we try to explore its quantum properties and its quantum behavior and try to see if anything exciting or different or unexpected happens.
Yeah, and so maybe a kind of very related question. Within your field of research, so since you've been active, what have been the most surprising and cornerstone discoveries and experiments? Oh,
okay, I can start. I think for me, it's really not one event, but it's a kind of an integration over events. Because if I look back to my studies around the year 2000, people came up, or we already had actually a little seminar on quantum computing, but it was something thought to be complete science fiction. People thought this is just not going to work. And there were even very serious theoreticians and experimentalists who had arguments why it cannot work for fundamental reasons. And now, 20 years later, we have people who managed to actually build these devices. So I think for me, the most amazing thing is really this really fantastic progress that has been made in technology, in quantum technology, I should say, by people like Yiwen, by the way, to actually control these systems and really make these quantum computers, which was complete science fiction, a real thing. I mean, we are still working on it, of course, but now I think it's pretty clear that it's real. So that's, I think, the revolution, which is sometimes called the second quantum revolution, that I think is really amazing.
Yeah.
Yeah, and I think for me, it's related, and maybe more specifically, I think for a long time, people have known that quantum mechanics apply to, very specific, isolated, small systems like atoms or electrons or things like that. But, since I started working in quantum science, people have really expanded the number of systems that we can really control as their quantum behavior, right? Like things in the solid state, materials that live in a chunk of material, right? It's not just a single atom floating in a vacuum chamber, which maybe you can think of it as somewhat, it's much simpler than, let's say, an electron or a circuit that's on a piece of material, which is, in the end, pretty messy and complicated, right? And yet, nowadays, like people they're not afraid of working with these more complicated systems, and they're able to make them behave quantum mechanically. We can measure how they behave. We can even control how they behave. And I think, it's really amazing that we can now work with these much more complicated objects still in the quantum regime.
Yep. And again, I have a questions for both of you. What is your proudest research outcome so far? Maybe Renato, again, you can get us started.
Okay, yeah, it has somehow to do with what I said before about exploring the limits of quantum mechanics. And I think so far, we have developed some thought experiments which tell us, or at least indicate, that there's a real problem when we do that, that there's a real inconsistency if we just take the rules of quantum mechanics seriously and apply them to larger and larger systems. In particular, if we apply them to systems that are large enough to be themselves systems that could think about quantum mechanics. So this is a kind of some people call that a Gödel type argument. You are asking yourself, can quantum mechanics describe someone who thinks herself about quantum mechanics? And this leads to contradiction. But this tells us quantum mechanics cannot be really applicable probably to larger objects, because we are, of course, ourselves a larger object. And I think this, for me, is a discovery. I'm really maybe not proud, but this I find the most interesting also for my future research. It will certainly have an influence on what I'm going to do in the next years.
Great. So for me, it's actually maybe a bit related to what Renato said, and also my earlier answer. I would say maybe one of my proudest accomplishments is an experiment where we showed that the motion of a material, a piece of material, which is not very big, it's maybe like a small. You could think of it as basically the width of a hair and about a millimeter long. You'll be able to see it. You can put it on the tip of your finger and you can see it. And the sort of the motion of all the atoms in this piece of material together, we saw the quantum dynamics of that. And this is obviously, it's not that big or complicated of a system. It's not going to think about quantum mechanics. So as usual, the experimentalists are a few steps behind what theorists are thinking about. But that for me was already a really, I think even on a fundamental level, a really cool thing that you can do that, right? And so this is relating to what I was saying earlier, that we were working with more and more complex quantum systems. That for me was a really cool thing.
That's really awesome. Okay, so I will start wrapping up this section, and I just have one more question for both of you, which is related to any advice that you may want to give to younger students. And so maybe Yiwen, you can try to go back in time and think about yourself as a high schooler. What advice would you give to yourself?
Yeah, I think what I would tell myself is that, as Renato mentioned early on, you get to work with a lot of really smart people who are smarter than you, or maybe, they seem smarter than you. And you, as you go on in your career, they will get smarter and smarter. I think I would tell myself to really appreciate that, but not be intimidated by it, to be confident, in my own abilities, and that, I think not to be intimidated by, let's say, people who maybe seem smarter or more confident, or maybe even more knowledgeable, right? And to speak up and not be self-conscious about asking questions, right? And because I think back then I was, maybe a bit more shy and self-conscious, and I think I could have, taken advantage of more opportunities, by putting myself out there more. And that's, I think that's a really important part of it, is to have that confidence to do that. And so that's, something that I think it's hard to I mean, maybe high school me would not have been so convinced or been able to actually do anything with that advice, but still, it would have been nice to hear it.
Great, thanks. Again, I sympathize a lot with your answers. And Renato, instead, let's say that you meet a bachelor student, a young bachelor student that hasn't yet figured out which path in physics to follow, what would you tell them?
Okay, yeah, so first, I think I would tell him he should be relaxed about decisions he has to make, because as I said before, I think there are many ways that lead to the same thing. If one really has an interest, at some point, people will work on that. I've observed that many times with other students who kind of made turns, and that at the end they really found the things that was most interesting to them. And of course, the interests are very different. And I think one can only be really happy in this job as a researcher if one really researches on something that is one's true interest. So I would just give the advice to look around, explore different things, and once you feel emotionally kind of attracted by one particular thing. I think there's a large part of emotion in research. In some way, it's not, I think, a really objective decision. What's the best research field? I think it's what excites you most, then you should do it. But I think one advice I would give to the student, which would have helped me in that situation, would be also to be more relaxed towards how one sees the material that one is taught. Because when I was taught physics, I was always thinking that this is really the truth of everything. There cannot be anything questioned. And now I realize that sometimes we are really pretending towards the students that this is all fixed, but it's actually not. I mean, there's, for example, in quantum mechanics, this famous measurement problem, which is actually at the very beginning, you could say we don't really understand how to model a measurement to the end. I mean, we know how to describe it mathematically, but if you think it to the end, we have a problem. And I think if I knew as a student about that, I would have been much more relaxed in some way, because I always, when I didn't understand how this all fits together, I thought it's my fault. And I never had the thought that it could be that something is really not understood by the whole research community. And knowing that, and I think there are so many questions like that, knowing that these are still open questions would have helped me.
Yeah, great. I hope that this advice will help the students in the audience or that will watch later this talk. And so at this point, I want to encourage everyone to think about questions and send questions in the chat. And in the next minute or so, maybe Renato, you can tell us a bit about the newly established ETH Zurich Quantum Center.
Maybe actually Lydia would be even the better person to talk about that. But
yeah,
no, I mean, I should say, okay, you know, I should give a little piece of history that Switzerland has been extremely strong in quantum technology already since many years. There is the QCIT, which is a Swiss-wide, it's a national, so-called National Center of Competence in Research. So what this means is there's a network of groups within Switzerland who are all doing research on quantum mechanics. And the amazing thing about this research we do in Switzerland in this field is that we are really extremely broad. I mean, if you now think about what could be the platform of a future quantum computer, is it ion trap superconducting qubits, something optical maybe, or something based on quantum dots or hybrids? We do all that research. Now, I think we also have to think of towards the future. And in the future, we will, of course, also have to scale up certain things. I mean, now we have explored all these different areas, and now we can ask ourselves, what if we really push something, if we, for example, build larger devices, for example, not only a 2-qubit chip, but a 50 or 100 qubit chip. And for that, we need a kind of, a framework around that where people connect. And as we heard before, I mean, we have to talk to each other and exchange and collaborate. And the Quantum Center at ETH has this goal in research, but it has a second goal, which is teaching and education. Of course, we will also need people who are knowledgeable about this whole field. We have also this new master program in quantum engineering at ETH. But in general, we want to teach people quantum mechanics, quantum physics, quantum technology, also the engineering aspect that is now becoming more and more relevant. And the Quantum Center also has that goal. So it's really kind of, we want to be ready for the future, to have a very good expertise in Switzerland, very well-educated people, and also very good research labs. And I think we are on a good track. And the Quantum Center has just started. You will certainly hear more about that in the future.
Great, thanks. And so now I will pass the word to Lydia, who will be moderating the questions from all of you.
Okay, so we already have 3 questions. There are 2 for Renato and 1 for Yiwen. So I'll start with Renato. This is a practical career question, which is, you did your PhD in computer science and then you came back to physics. How hard was this transition, and how is it these days to navigate between these disciplines?
Okay, yeah, that's a good, interesting question. So for me, it happened a bit automatically. I was actually, as a physics student, getting interested in quantum computing at that time. And at that time, there was simply no one in the physics department who did any quantum computing. There was also no one in the computer science department, but there was a very visionary professor, Professor Klaus Hepp, who told me I should just still go to the computer science department and tell them that I want to do it. And I went there and told a professor there, my future supervisor, Willy Maurer, that I want to do quantum computing. He said he doesn't do anything in that direction, but if I'm happy to work independently, that's fine for him. So in some way, I paid the price of working essentially at the beginning without a supervision, which was also, I mean, of course, he helped me wherever he could, but I didn't have someone in my field. And that was not too difficult because it was very quickly possible to establish collaborations and exchanges, for example, with people in Geneva who were already doing that. So in practice, this move was really, for me, I think, a very good experience. It was very easy to connect to people at that time. But at that time, the field was very young. Then moving back to physics, I think this was not hard because once you have, I think, studied the discipline, you always feel somehow home there. And it was a bit like returning home for me. But how is it today? I think today it's getting hopefully even easier because there are more and more institutions who realize that they need to be interdisciplinary. And sometimes it's even a requirement on positions that they are interdisciplinary between, for example, computer science and physics. So there are more and more positions like that. So I think the market for people who really understand both is in some way growing. There is still a problem in practice, I have to say. So there are still in certain institutions or in certain heads of people, the idea that if you, for example, apply for a job in computer science, then you need to have publications in a computer science journal and vice versa. And this is sometimes an obstacle. I think this is also improving at the moment because we have also more and more, let's say, also venues where you can publish, which is not clearly associated to computer science and physics. And so I think it's just a matter of time until this boundary between the two fields gets smaller. So I would really recommend, so maybe I should end the question or the answer with a recommendation. I would recommend to people who are interested in both to really also try to learn from both areas and not think that this could be a disadvantage. I think in the future, I'm pretty convinced it will be an advantage.
Yeah, very good. Thank you. We have a question for Yiwen from YouTube this time. How do you see the role of academic groups in quantum research compared to all the startup and industrial efforts popping up at the moment?
Yeah, that's a really good question, and one that I spent a lot of time thinking about as well. Well, I mean, I think there is, I mean, you might wonder this, right? Because of course, a lot of the industrial efforts, they have a lot of resources, they have more people who work there for longer periods of time. And I think that of course is a very valuable, let's say, addition, right, to our field, because there are things, right, that require people to work on them for a long time and have a continuity of knowledge or skills. And these are things like, for example, building more and more complex quantum technologies. When Renato mentioned earlier, this idea of scaling up quantum technologies, and there's a lot of engineering and trial and error and things like that that are involved. And there, I think you know, these industrial efforts, these startups and large companies, you know, they really have you know, a lot of the resources that are required for that. But on the other hand, you know, I mean, academic groups are, you know, we are more flexible, right? We can come up with new ideas and change directions in our research. And there's also, I should just make it clear that there is a lot of fundamental science still to be done in quantum science. It is not just a question of engineering at this point. And we don't know in the end, even on a very basic level, what will be the system that works best for a quantum computer or a quantum network, right, or any of these applications, right? And I think the flexibility of an academic group, right, and the ability also for you to work on many different things and be exposed. Also, I think it's not so much necessarily the academic group, but also the academic environment, right? You get to talk to more people who work on related but different things, right? At ETH, as Renato mentioned, there are people working on all kinds of different systems. You broaden your horizons and your overview of the entire field. And I think that's still a really important thing right now, right? Not to say, okay, this is, you know, most of these industrial efforts, they focus on a particular system. But if you really want to, I think, be a researcher with a broad overview of the field, you can only get that in an academic environment where you can talk to other people who work on very different things. And I think that's very important still.
Yeah, thank you. I think indeed that's a very, very important point. So there's a question for both of you, which is, how do you try to increase the diversity of nationality within your research group? Do you search for students from the Southern hemispheres, or do you focus on European students first? And how could this be addressed in the physics community? Because most of the resources are, say, in Europe, North America, a few places in Asia, Australia, but there's talent everywhere.
Do you want to
Maybe I could say there is a big challenge coming with that, because if I, for example, want to hire PhD students, I need somehow, I mean, the first thing I need is kind of a reference. I need someone who tells me this student is really good. Now, it's because it's very hard to assess people from the far. So I think as an individual research group, I can really do very little for this assessment. I cannot invite people from all these countries far away to come here and to have an interview. So the best thing would be to have somehow an assessment there in some way, which is of course not something I can organize as an individual research group. So I think this is really the challenge. The assessment of people in other countries is very hard to make. So usually, I mean, my group is still, I think, very international, but usually this works via people who are already, for some other reason, in countries where I have connection points, people who can tell me this is really someone great who would work well. So in that sense, I think there's a lot still to do, because I see that with that scheme that I'm following, students from certain countries have almost no possibility to enter into that type of research. So I think in that sense, we are not doing very well. And it would certainly be worth thinking about measures to increase our, let's say, field of students we can possibly assess and then also take.
Yeah, I mean, I think, well, so maybe to answer the first part of the question, of course, it's a similar issue as what Renato mentioned, right, is that there are certain areas that I'm more familiar with, and it's easier, right, to know, whether a student has the right background. And I think for me, there's definitely not a focus on Europe. I did most of my studies in the US, and so I hope, right, that we keep an open mind, and that and our group is quite diverse, actually, in that sense. But I agree with Renato that it's a difficult but important problem to work on. And I also agree with Renato that a lot of times what really it comes down to is a personal connection, right? Like, somehow meeting this person or getting to know them a bit better than just oh, I got an email with a CV, right? It's, based on that, it's oftentimes very difficult to judge. So I don't know. I mean, maybe we should organize more conferences in countries where, you know, we don't already know a lot of people, and invite students to join and to talk to us at those conferences and things like that, right? That maybe is an opportunity, right? Because maybe in a lot of places it's maybe hard for the students to go to, you know, international conferences that we usually attend. And so, yeah, but that's a really good question, and I think an important problem to address.
Yes. Very good. Yeah, so there's several questions, by the way, Renato, about your result that you talked about. This is consistency of quantum mechanics. So maybe you'll have to give another talk just about this.
I will actually give a talk later today in a colloquium.
Very good. So then I will try to find the link and post it on
yes, it's the Galileo Galilei Institute in Italy, and they invited me to give a talk at, I think it's around 5 or so, but I can send you the link.
Okay, very good. So but one question is about the process. So the question is, you received quite a bit of pushback about this, and how was this process for you of dealing with this pushback? I know you're very busy answering emails for a few months.
Yes, yes, indeed. When this paper came out, I was essentially flooded by emails and also real mails even. So I think Lydia once saw the staple of conventional mails on my desk. Yeah, it was kind of for me a nice social experience, because if you make the claim that quantum mechanics gets inconsistent on larger scales, you cause a lot of reactions. And it took some time until people somehow even started to think it could be correct. And then, so yeah, for me it was like really interesting how this result kind of diffused into the community. First, there was a lot of resistance, and then after enough important people said it's probably correct, people started to read it, and now I think it's more or less settled in a certain, I mean, people may still disagree with certain assumptions and so on, but it's kind of really on a scientific level. At the beginning, the discussion was more on a, I would say, almost non-scientific level, surprisingly. I got many emails which I would say were not on the, let's say, level on which scientists would discuss. So yeah, I think it was interesting to observe that. Probably one could have made a social study of what happens if a new result comes out, and how do people take it up, and what's the situation after a few years. I think one could have learned a lot from that study. Maybe one could still make it.
Okay, so here's a question for both. Maybe we can start with Yiwen. Would you say that in your position you have enough time to actually do research, or are you too busy with other things like teaching, meetings, supervising, traveling, admin, etc.? And do you think this is a general problem that should be addressed in universities?
I mean, I would actually say that at least at this point in my career. So again, I just started my as a professor 2 years ago or so, and I don't know exactly how it works at other places, but at ETH, it's actually really, I feel like I have quite a bit of time to do research and think about, and go to the lab, sometimes even do things there and think about my research. I only sort of teach half of the semesters, which is really nice. It's sort of generally the case for assistant professors. And so I'm really trying to take advantage of this opportunity. I know that these obligations sort of ramp up later on in your career. But I think for now, it's really, really quite reasonable. And again, those are important parts still of being a researcher, like teaching and supervising and going to conferences and talking to people, right? I would say that those are not sort of orthogonal to doing research. And so as to whether it's a general problem, I don't know. I think it really depends a lot on I think it works differently at different universities. But I do think that, maybe one thing that will help is, I guess being a professor is kind of this weird job where you get trained for like one very specific part of it for a long time. And then all of a sudden you have these responsibilities where I think very few people get actual real training on that, in other professions would be unthinkable, right? Like you manage a team of people, but like, you know, you don't necessarily aren't required necessarily to get training on that, or you start teaching, and that's the point at which you're told, oh, you should, like, you know, go take these courses and learn how to teach. And so maybe, you know, those things could become more efficient if we, you know, if we paid, you know, more attention to that earlier on. And maybe, I mean, that's maybe one strange thing about the system in general. But you know, you just have to adapt very quickly, I guess.
And Renato?
Yes, so I think if one doesn't really pay attention, it soon happens that you would not do any research any longer. So it's clearly something one has to actively oppose. And I think I don't need to give that advice to eventually knows that, but probably to all the younger ones. And it's not necessarily tasks at ETH, it's actually tasks within the research community itself. And there are networks within the community. And even as a young professor, you're asked to be the director of that network and be involved in this committee and do that. And you have to learn to say no to all these requests. I mean, not to all, but to many of these requests, to the majority of these requests. Otherwise, it would indeed end up doing admin tasks, I would say. I mean, admin tasks maybe not uninteresting tasks. It's interesting things. It's maybe about strategy and really bigger questions, but they're not research. I think if you now define research not only to be the time when I'm actually really myself doing a calculation, but also actually when I, for example, prepare a class in teaching, I sometimes see certain connections to stuff that I do in research. And then during this preparation, I think about these research questions. So if I see this bigger picture, and of course, discussions with other people in research is anyway research. So then I would say it's actually quite some time one can still spend for research, but it's a constant fight against all these other requests. But to be concrete, I would say if I count together the time in a week that I can really think about interesting questions in one way or the other, then I would still say it's the majority of the time.
Okay, so because it's already 1, I'll take only 2 more questions. Okay, maybe this one is easier to answer. In the scope of advice for young students and researchers, is there any habit you've developed or technique you've used in the last few months that helps you do better science in the times of the pandemic? Anyone?
I have to think about this a little bit. Renato, do you have?
This is a hard question. I would also have to think.
Yeah.
So, yes.
I mean, I guess one thing that we had to do definitely during the lockdown was we maybe became slightly better theoreticians because that was, you know, we couldn't physically go to the lab. And so, you know, it was an opportunity to maybe think a bit more deeply and answer some of the questions that actually we've been putting off in our research. So I think just in general, you know, being more flexible and adaptable and like taking a step back and looking at, you know, what are some things that maybe were in the back of our minds, but we've been too busy doing other things, and now we can think about them, which is kind of nice, actually.
Yeah, maybe what I would say now after reflecting a little bit is that whenever there is a change that disrupts your life, you start to question certain things that you always did. And I mean, for example, do you really spend the time on the most important questions and so on? And I think the pandemic motivated me to even more think about these questions. Do I really invest the time into the stuff that I want to do at the end and not into stuff that just comes up? But I don't think this is specifically pandemic related. It's just, it was a trigger for me to again go back to these questions, and maybe one should ask them more frequently oneself, because one gets, as I said before, easily distracted by all the requests and things, and at the end ends up doing maybe even research projects that if one looks at the bigger picture, one would not have done, and rather focus on maybe a different one that is closer to one's heart.
Mm-hmm. Okay, there's one question. So we know how in physics we have this kind of mythical cult of the genius, and in particular of the young genius. And there's this idea that you have your most important research ideas in your 20s. So I wanted to ask you, or the audience wanted to ask, at what age, at what point of your career did you have the most haha moments?
So, I mean, actually, you know, I think I learned a lot of my physics knowledge when I was younger, for sure. I mean, you know, when you take your first physics classes, you sort of absorb knowledge at a very high rates. But I think for me, a lot of times the aha moment is realizing the connection between different things and what you've learned. And that happens much later on, right? So for example, when I taught my first class last year, that was when I realized like I kind of knew all these different things, but I hadn't really put everything together and they weren't really connected in my mind. But when I really had to sit down and think about like, how do I make a coherent, logical syllabus for this class and explain to the students like why we're talking about this and how everything is connected, that's actually when I understood a lot of new things. So
I think my answer is almost the same. I think I learned most of the stuff really fundamentally when I taught them. And of course, as a student, I didn't have really the opportunity to teach, and now I have it. And I think there are many more moments now where I think, okay, now I finally see why this is like that, or now this makes sense. So if you ask when are these aha moments, I think there are many still. And I think there's a difference between physics, maybe, and mathematics in that respect, because indeed in mathematics, we know that many of the big insights come very early on. I think in physics, we still have a lot also to learn. There are lots of stuff that has been developed that somehow all fits together. Whereas in mathematics, there are these different fields where if you do number theory, you don't necessarily need to know everything about differential geometry and so on. But in physics, I think having the big picture helps a lot because, as I said before, even information theory is connected to thermodynamics. And now I think quantum mechanics is, of course, also coming in that respect. And to acquire all that knowledge also takes some time. And we constantly learn still as a professor, we're learning a lot. And the more we learn, the more we can make such connections. So I don't feel that it's really as a 20-year-old that one could I could have made much progress.
Thank you. Yeah.
I think we will wrap up now. And I want to thank you very much, Yiwen and Renato, for making this event very inspiring and very interesting. And all of you from the audience for joining us today and for participating and being so engaged with the talk. We will put out this talk on YouTube later on, so you will be able to share it with everyone you know. And on behalf of the Quantum Center at ETH Zurich, we hope that you enjoy this event and you will join us again for any upcoming activities. You can follow us on the website, but also on the social channels, Twitter and YouTube, to stay in touch with the activities. And on behalf of myself and Lydia, I wish you a wonderful rest of the day. Thank you very much.
I'll just say one more thing is that our next event will be in about 2 weeks, and it will be about how to do a quantum startup. So we'll have more information soon. Have a good day.